Let's talk about analyzing an AC circuit with complex numbers, real and imaginary. So this is a standard equation for a sine wave, and this could be either in voltage or current. And if we take the current, we divide it into voltage, we get a result that's related to the circuit's impedance. Okay. Now these types of equations, they're difficult to solve. So we're going to use complex numbers to make the math easier. So down here is our complex plane. This axis here is real numbers, and then our imaginary run in this direction here, with the inductance going this way and capacitance running down this way. So we know what real numbers are. What's this imaginary number? Well, they realized that if there was a number multiplied by itself that equaled -1, that would be useful. So, we have to find what the square root of -1 is, okay? Well, that just can't happen. 2 times 2 is 4. -2 times -2 is 4. You're not going to get a minus over here. There's no two numbers multiplied together that's going to give us that. So we're just going to imagine a number that can do that, okay? So mathematicians, they use the letter I for imaginary. I was taken for amperage or intensity, so we use the smaller case j. So what does this number do for us? It allows us to rotate a phasor in our complex plane here. So if we multiply by j, then we rotate it 90 degrees up this way. And if we multiply by minus j, we're rotating the phasor down this way by minus 90 degrees. Okay, so let's take a look at an inductor and a resistor. This has an inductive reactance of 7 ohms, and the resistor is 7 ohms. Okay, so we're going to plot that on this chart here. We take our real number across here, 7, and then we go up this way, 7, and we come to this point here. This is going to be the rectangular notation for that is going to be 7 plus j7. That's that point there. Now this phasor that we draw up here, that distance there, that's our impedance. So in order to get the impedance, we can just use Pythagorean's theorem. This is a right triangle. So it's over here, we get the square root of the imaginary number squared times the real number squared, and we get our impedance of about 9.9 ohms here, okay? Now, this is our rectangular coordinates, or rectangular notation. We want to put it in polar coordinates also, because adding and subtracting rectangular notation is easy to do, but for multiplication and division, it's easier to do it with polar coordinates. So to find our polar coordinates, it's just the phasor here, which we already figured out, which is 9.9, the magnitude of that, and then this angle here. To find that angle, we just take the arctangent of the imaginary divided by the real. In this case, 7 divided by 7 is 1, and the arctangent of 1 is 45 degrees. Now on your calculator, the arctangent is going to be the tangent to the power of this -1. That's what it's going to look like on the calculator. So let's try a real case situation here. We've got a voltage source. We got 10 volts RMS. We've got 60 hertz. We got a 10 ohm resistor in series with a 220 microfarad capacitor. So to find the capacitive reactance here, we just use our formula here for capacitive reactance. At 60 hertz, it comes out to about 12 ohms. So we plot this over here. We go 10 ohms across here, and we go 12 ohms down this way. And this point here is going to be 10 minus j 12, and that's our rectangular notation. Now, to find our impedance, it's just this length here. We use Pythagorean theorem again, and that comes out to about 15.6 ohms. Now, to find our polar coordinates, it's just 15.6, and we need to find our angle here again. So that's just the arctangent again of the imaginary divided by the real, and it came out to minus 50 degrees. So our polar coordinates is going to be 15 at an angle of minus 50 degrees. Okay, so now we want to find our how much current's going through here. Now you can just divide it out with polar coordinates, which I did here, But you can just simply take your RMS value divided by the impedance here, and it comes out to 0.368 amps. Okay. So we want to test this circuit, and so we have a 220 microfarad capacitor here. Now this is an AC capacitor. You can't use an electrolytic capacitor because they'll blow up. You can't put them on AC. Okay. So this one's good for AC. We have a 10 ohm resistor here, and this is a 0.1 ohm resistor. I'm using that as a current shunt to monitor my current there. Now I put this on the scope, and I want to find the phase difference. Okay. So in order to do that, we take the cycle time. So it's 60 hertz, right? So from peak to peak, it's going to be 1/60th of a second. So that's going to be 16.67 microseconds. And then on the scope, I'm going to put a couple cursors where the current and the voltage crosses the 0 point, and I'm going to put my cursors on there, and it automatically tells me the time between there is going to be 2.3 milliseconds for that. Okay, so the current should be leading the voltage. So I'm going to put it up on the screen, and we'll take a look at it. And it does come out to, when I calculate it out, it comes out to 49 degrees. So it matches up with this over here. So I'll leave you with the scope, and thank you.